I would like to welcome you in this webinar about the latest developments in ANSA and Meta in the durability field. So today we are going to start with ANSA, and we will see enhancements regarding contact definition, some new capabilities about the Abacus step definitions inside includes, enhancements results in the results mapping, and the new cross-section solvers. Then in Meta, we are going to see the modal to random response with the use of MetaDB, and the new ODF toolbar, which is the implementation of the openings distortion fingerprint method for the stiffness body stiffness evaluation. We will start with ANSA. The new developments will be shown through slides, and parallel we will have a live demo. So starting with Abacus contacts, the contact info option has been added in the context menu of the contacts list. This option will evoke a window that hosts the contact's attributes as well as the related entities that are used by that contact, such as friction, surface interaction, controls, and so on. In this way, we have a better overview of the contact definition and all the associated entities. Moving on, edges are now introduced for the contact definition through the Contact Assistant tool for Abacus and ANSYS DEX. The contacts can be defined either by picking the cell edges for primary and secondary surfaces of each contact area, or they can be detected automatically by proximity. Additionally, the node to surface contact definition is also available through the Contact Assistant tool, and it can be defined again by picking the respective entities or through an automatic detection based on proximity. The aforementioned contact types are also realized through the contact FE representation of ANSA SimWorld connections. Specifically, the feature line to feature line edge pattern will create edge-to-edge contacts, and the feature line to flange pattern will create node to surface contacts respectively. So let's see that in ANSA. So here I have a 2D model, and I will define through the Contact Assistant edge-to-edge contacts for the top and bottom parts of this model. I will do this first manually. I will isolate the top part, select the edges with the feature selection, bring the other part, select the other edges, and I can see that the contact is created. I can edit the contact of the card of the contact, add the surface interaction, and press finish. The automatic detection works on the selected cell elements and based on the proximity. Oops, sorry. Okay. And based on the proximity, it will identify the candidate contact areas. I can inspect the contacts that have been identified, and by pressing finish, I have the contacts defined in an automatic way. Let's see now an example of this edge-to-edge contact through the SimWeld FE contact FE representation. I will select this to I have here the feature line to feature line search pattern, so it will search for the edges, and I will create contacts. I can specify a contact ID if I want, or I can create a single contact for both SimWeld. I will press realize, and I can see that the contacts are created here. Moving on, let's also see the node to surface contact definition. So now I will open the contact assistant. This time I want a surface node. I will select the automatic detection, select the area, specify the distance, and I can inspect what it has been identified as contact. So I have the two contacts defined, and as we mentioned, I can go to the context menu of the contact list, press info, and I can access this view where I'm prompt to edit the contact or the sets that are used by the contact, and add the related keywords for friction, surface behavior, contact controls, etc. So every entity is hosted, every entity related to the contacts is hosted under this tab. The same example with the solid, with the SimWeld. Now the search pattern is feature line to flange. Pressing realize will create the contacts between the two parts. Okay. Moving on, the solid bolt FE representation for bolt connections has been enhanced with the automatic generation of contacts. So during realization, contacts between the head and the top part, between the top, between the head and the thread, can be created and realized with the connection. This enhancement is available in Abaqus, ANSYS, and Nastran-X. Additionally, the same FE representation can now create also the bolt pretension entity along with its boundary condition. So once the connection is realized, the pretension entity is created for the bolt. Let's see that. So here I have this model. There are both connections defined in my model. I will select these two. And as you can see, this is the solid board representation. Here I have the options to create the pretension. In this case, I am selecting the Abacus pretension. I also select to create the C load at the specific step, and also specify the magnitude of the C load. And on this area, I can select which contacts will be created. Contact between the head and the top part, and the contact at the thread. So pressing realize. Okay, I can see that the boards are created, and the contact definition as well. So there is a tie contact on the thread, and a contact pair between the top and the flange of the part. Respectively, the pretension sections are created, and the C loads as for the pretension load. So the following enhancement has to do with the Abacus step entities inside includes. Up to now, it was not possible to add step entities inside includes. Now, when a step entity is added inside an include, all the history data entities in this step are also added in the include. Those entities can be also added to separate child includes inside the step include. Changing the order of the includes, the step includes will also change the order of the steps in the step manager and vice versa. Finally, before output, the model data includes will move to the top of the to the top of the includes list, so they are written first, and the history data includes are written last. So they are valid for Abacus. So let's see an example in ANSA. So here I have a model. I will open the step manager. For this model, I have defined 3 steps. Every step has its boundary conditions and loads. And if I open the includes list, I have also defined two includes for step 1 and step 2 respectively. I will create a new include for step 3. Okay. Now, and I will add the include the step 3 inside this include. Okay. So as you can see now, during the creation, the include took the ID 3, so it's on the top of the includes. So if I go to the step manager, I can see that this action also passed to the step manager. So the third step, the step with name step 3, passed at the top. Now, if I bring it here, you can see that automatically the includes list is updated. So to ensure that it will be written, so to ensure that the includes will be written in the respective order. Now, inside this include, I will create a new include with the boundary conditions of the step 2. So I will go to step 2, select this C load, drag it to this child include, and as well the boundaries. Okay. And now I have an include with the contents of the history data of the step 2 inside the step 2 include. I will also create a model data include with the elements, the material and property. I will add an ID 10. Okay. And I will output this model. Okay, as you can see during output, the model data include moved to the top. So it will be written first and be valid for Abacus. Now, if I see what is written, I have the main file. The model data include is written first, and then the includes with the steps follow. For the step 2, also, I have the step definition inside this include, and I have also an include reference to the BCs of this step 2. So if I go here, I can see that this include contains the boundary and the C load of the step 2. Next, we have the results mapping enhancements. The mapping of results on integration point over thickness is now available through the results mapper entity. This type of mapping works on both cells and solids, and the results on integration points can be selected for both the source and target model. This feature is available only with the radial basis function, the RBF mapping method. Let's see an example. Okay, so I have this model. This model is a solid model. I have some rows of solid elements, and what I want is to map the initial strains from a dyna, a model, cell model, where I have the initial strain defined through the thickness into 6 integration points through the thickness. So every cell element has this information, and this through the thickness information will be mapped with the use of the results mapper. So I open the results mapper. I'm selecting the Dyna file, the source model, and I will map the plastic strains. So I will use the RBF method, and I will pick here the source location from integration points. So this will take the mapping, the data for mapping from the integration points of its element. The target location is will remain auto, so this will map the interpolated. This will map the interpolated value into the centroid of its solid element. And if I press OK and apply, I can see that the tool has created initial condition type plastic strain for Abaqus, and coming from the values of the integration points of the cells. Okay. Moving on to some enhancements regarding the meta results plugin. It is now possible to map multiple meta states and assign them to corresponding Abaqus steps. This is done with the option All in the state drop-down menu, and this will perform the mapping for all the states, and all the created entities will be assigned to the corresponding steps. This option is available only if the results that come from Meta can be mapped as history data, so they can assign to different steps. Continuing within the same plugin, the deformed geometry of the selected state can be used as a source model in order to have more accurate result mappings. Sorry. Okay. Okay. Sorry. Finally, the mapping of equivalent plastic strains is now supported by the Meta Results plugin. Specifically, the certain labels that are recognized as equivalent plastic strains in the MetaDB uh, are used for the mapping on the elements centroid, and after the mapping, the appropriate solver entities are created for Abaqus, Nastrand, LSDyna, and Radius. So let's see all this in ANSA. So I have this model. And I have also deep drawing analysis that is performed on this part. So from this analysis, I will map the equivalent plastic strain and the stresses through the results mapping plugin. So I will open the plugin. I will select the MetaDB with the stresses. Okay, the MetaDB is read, and from the stress components, the tool is going to create Abaqus D loads. So I can select which state I will read, or I can select all. So this will create, this will do the mapping 11 times, and will create D loads and assign them into 11 different steps. Pressing next and selecting the property. The mapping is taking place multiple times for each state. And by pressing finish, I can see that it has created 11 steps, and the respective deload entities for each step. Let's see now an example with the mapping of plastic strain, equivalent plastic strain using a deformed geometry. So in this case, I have the same model, but now the model is deformed. So I have selected a state that my shape is not the initial, but it is deformed. So I will do the mapping. I will select the MetaDB with the equivalent plastic strains. Note that the name of the label must be one of the EPS equivalent plastic strain or PEEQ. So let me show you again. So the name of the label in Meta must be one of the three, so that is recognized by the results mapping plugin. Okay, as you can see, the tool will create initial condition type hardening. I will select the state here. If I go down, you can see here that the all option is not available, and this is because the initial condition type hardening is model data and not a history, so I cannot assign it to a step like we do previously with the deloads. So I am selecting the state 7, select the connectivity, and I will select here the used geometry, the deformed geometry as the source. So if I see here in step 7, the geometry is deformed. So in order to have a matching between the source and the target, I need to specify this option. Okay, the initial conditions are created. And they are mapped according to the deformed geometry. Finally, the cross-section tool of ANSA has been enhanced with the new FE2D solver. This solver calculates the cross-sectional properties for both thin and solid section by performing an FE2D analysis. Additionally, the calculation of cross-sectional properties for non-homogeneous solid cross-section is now available with the FE and the FE2D cross-solvers. So now performing a section cut or a multicut on a non-homogeneous solid part using one of the FE or FE2D solvers will give the cross-sectional results considering the different materials of the solid part that is being cut. Let's see also an example. In ANSA. Okay, so here I have this solid beam model with two properties. So on the web I have aluminum, and on the flanges I have steel. If I do here a cross-section cut, I will select 3 points to define the cutting plane, select the elements that will be cut, and the important is to select one of the FE or the FE2D crossover. So by selecting the FE, I get the cross section, and if I switch to the cross menu, I can see that the non-homogeneous cross section has been calculated. The reference material is the aluminum, or the steel, so all the properties are calculated based on the reference material. A new option here is available, so for the solid cross section. So if I open here the shadow, I can also see how this solid cross section looks like. Okay. Now continuing with meta, the model to random response analysis has been facilitated with the use of MetaDB. So starting from modal model, we can use the modal response tool to get the stress FRFs and output these results that are calculated by the modal response tool into a MetaDB. Afterwards, using this MetaDB and a PSD input, we can calculate the stress PSD with a random response tool. Let's see an example in Meta. So this is the analysis with the modal stresses of this model. I will open the modal response tool, and I will select the OP2 with the model results, select all the modes, and switch to the frequency response to calculate the FRFs. I need to define a load So I will pick a node from screen that the load will be applied on. Okay. The load will be at the degree of freedom Z, and I also need to specify a frequency range. So starting from 1 to 600 Hertz. Here I will specify the where the calculation will take place. So I will calculate for all the elements of the model the full range on the full tensor on the frequency range that I have specified. I want 3D results, and if I switch here to the settings and the file output tab, I have here the option to output this in the MetaDB. So I will create a MetaDB. I will also save the geometry, and if I press calculate, the results are calculated, the FRFs are calculated and are saved in the MetaDB. Now, if I open this MetaDB, I can see the stress FRFs for the frequency range that I have specified. I will read them in. And then I will open the model response tool. The random response tool. Okay. The MetaDB is red. Sorry. Let me open again the MetaDB. Okay. Random response. Okay, here the states are red in the random response tool. Here on the next tab, I need to define a correlation, the correlation table, and the PSD input. So I will read the PSD and preview it. So this is my PSD. Since I have only one input, the correlation table will look like this. Okay, and once I have specified the PSD, I will calculate the stress PSD based on the FRFs and the PSD input. Okay. Once the results are calculated, the result for a node will look like this. So this curve is the stress FRF. This is the PSD input, and this one is the PSD of stresses from the random response. Moving on, we will see a new toolbar that implements the open distortion fingerprint method. The ODF method evaluates the stiffness of the body based on the distortion of the closure openings. Every opening has two diagonals defined, and each diagonals is defined by two nodes. The method calculates the distortion of each diagonal, which is the relative deformation between the two nodes, and the displacements of the diagonals that may come from transient FE analysis or multi-body dynamic simulations or even test data are used to calculate the distortion signal. So once this difference between the two diagonal nodes is calculated for its closure, it is evaluated statistically. And a bar chart or an over frequency range plot is created. These plots are the opening distortion fingerprint, and this is a characteristic identity of each vehicle, which is directly comparable with simulation variants and test measurements. Let's see an example in ANSA. Okay, so I will open a model. This model contains the diagonal definitions, and for demo purposes, the diagonals are represented by those beams and CBUS elements. The important here is that the relative difference between the two nodes of the diagonal of each closure is calculated according to a local coordinate system and the z-axis of this local coordinate system. So the geometry that I'm loading contains the coordinates, the local coordinate systems for each closure, for each diagonal of the closure. So the toolbar is accessible from here. First of all, I need to specify the unit system for my calculations, and then I can specify simulation data. So I specify the directory with my simulations. As we saw, the simulations can be FE transient analysis or multi-body dynamics analysis. And I can also have UNV test data. So in this field here, I specify the test data directory. I need also to specify the unit system for the simulation and the tests. And in this directory, I have one simulation, one punch file that actually contains the displacements of nodes of the diagonals, and one test for the respective closures. So a mapping file is necessary so that the nodes will be assigned to the corresponding closures. So if I open this mapping file looks like this. It has the name of the closure, the node IDs from the CAE model that define the two diagonals, the IDs of the channels in case we have tests. So these are the channels from the test data, and the measurement if I have a multi-body dynamic solver. Okay. So the displacement component is calculated according to the Z axis of the local system. And the statistical evaluation can be done with RMS or with this statistical evaluation parameter, which is actually the mean stress of the highest of the 30% of the highest values of the signal. On the bottom side of the window, I have the low cut frequency and the high cut frequency. So I can cut the signal. These actually are the low filter and the high filter for the signal of the distortion. So once my parameters are set, I can press the max bar chart, and the ODF will be calculated for both the simulation data and the test data. Okay. So here I can see the distortion signal. This is for the tests and the simulations, and this is the distortion of each closure. So it is actually the relative displacement of the two nodes in the z-axis, the two nodes of its diagonal, and the ODF bar chart looks like this, and I can see the fingerprint for the simulation and the test. So I can also see the behavior and compare the behavior of the simulation and the test. The cutoff diagram will calculate based on the relative distance distortion signals will also calculate the frequency content of its closure. It takes some time, so let's see that here. On the frequency range that we have specified, we can see how the content of the signal of its closure, which frequencies are playing a role in our signal. So these are the frequencies, and from 5 to 75 for its closure. Okay, so this concludes the presentation.